Welcome back to this session where we'll continue our discussion on the external flows of the fluid mechanics. So, in this particular session, what we'll do, we'll look at the boundary layer. I mean, essentially the flow, external flows, and the boundary layers. And once we discuss about those, and then, uh, as I pointed out earlier, we'll quickly touch upon the um, turbulence and the property of turbulence a little bit before we wind up discussion or on fluid mechanics. So that then after that we'll move to the topic of um, winds and all these things. Okay. Now, well, if you recall your dimensionless Navier-Stokes equation, so that looks pretty much similar to that. What is important to note here is that you end up getting this Reynolds number sitting here. Okay, and this is your momentum equation, and this is your continuity equation or mass conservation equation. So obviously, I mean, one can solve these equations, then you get a complete spectrum of the flow features, whether it's an internal flow or the flow around external object, whatever it is, you will get that. Okay. What is there in this equation if we drop the viscous term, which is this term, then it becomes an kind of it's an Euler equation, so which is known as the potential flow equation. That means the flow doesn't have any viscous effect. Obviously, the potential flow solution predicts zero drag or lift for all object, which is a phenomenon known as D'Alembert's paradox, because that is something not possible. That's a, I mean, that's why it is known as the paradox. Now, coming back to the flow over flat plate. So here is an infinitely thin flat plate. So you have this uniform flow. Okay. And then if you try to solve potential flow, what will happen? The flow over the plate would be slipping over, which is not as such possible. What is possible when the flow is passing over the flat plate, you can always have this kind of a boundary layer profile growth. And inside this small region, you'll have viscosity dominated situation, and at the wall there would be no slip condition to be satisfied. So that is where obviously this, when the flow passes over this plate, this region, these are always viscous dominated. But beyond that region, when you come outside this, where the potential flow assumption may be valid. So the boundary layer, what it is known as a very thin layer close to the solid surface where viscous effects are dominant. So when the flow passes like this, the uniform flow passes over a flat plate. This is the growth of a, so this is known as boundary layer. So in this region, you'll have viscous effect, which is going to be dominant. And this idea was introduced by Prandtl in and his co-workers, and this is a very, very important concept or finding in fluid mechanics after Navier-Stokes equation. This allows us to look at the flows close to solid body and allows us to characterize the behavior and things like that. It's an, as we said, that the boundary layer is an thin layer which is close to the solid surface. where the viscous effects are dominant. So outside the boundary layer, flow remains largely inviscid and there. So this is a uniform flow. Again, you can see the uniform flow which is coming in, and this is where the boundary layer grow, and this region is viscous dominated, where and the outside that one can have potential flow challenges. Obviously, this is the boundary layer thickness, where Prandtl showed that delta X is also quite less than the length along the streamline or along the flow direction. That we can see how that varies and things like that. So, which is very common in the fundamental of the fluid mechanics, and which has been taught in both undergraduate level and sometimes in the postgraduate level. What you can see is the laminar boundary layer over a flat plate. So if there is a flat plate, we have a flow. So the laminar boundary. So this is called the laminar boundary layer profile goes, and this is something probably close to turbulent boundary layer profile. The difference is that you can see the boundary layer thickness. This case it is quite large. This case quite small, and you see the profile velocity profile. There is a significant difference among that. Obviously, one case you have sharp gradient, other case less gradient. So once you have that kind of differences, it's going to lead to your skin friction coefficient and the stresses due to that. Obviously, at a given x location, if this is the direction, the Rex leads to thinner boundary layer thickness. So the boundary layer thickness at an at a thickness of delta, where you can the U would be 99% of the free stream. So the boundary layer thickness, this thickness is called delta. So the thickness is defined such that just at the edge of the boundary layer, the velocity is going to be almost 99% of the free stream velocity. So if we continue our discussion, as we have already seen, so we can see that the boundary layer over a flat plate, how this grows. So you have a uniform flow coming in, then this is the point over which the flow profile grows, and along this is the direction x, and this is the delta x, because here the boundary layer thickness is different than here the boundary layer thickness. So delta is also a function of x, because at different location, obviously that depends on other parameters like Reynolds number and such things. So what boundary layer does, it just shifts the streamlines upward. So this is what the streamlines is supposed to be. So it's shift the streamline upward. And there is a displacement thickness which is called delta star. So one can find 0 to infinity, 1 minus uy. So from there you can find out that thickness. Now this flat plate boundary layer, where you use the free stream velocity. So h is the initial height. So h is quite larger than delta. Then what we can find out that at x equal to 0, so it's essentially doing the mass balancing. So at any particular locations, we have h plus d. So h plus d, if I do, this is what I get, and that's what I get the calculation for displacement thickness. So that's, I mean, it's assuming a control volume like this, and that control volume one can do the mass balance. And if you do the mass balance, this is what you get. Because conservation of mass or continuity equation is something is very, very fundamental. Now, continuing with that discussion, so if you have this flat plate and the boundary layer profile grows here, then I can find out, obviously, what it does is that boundary layer actually causes some momentum deficit, unlike potential flow. So I can find out how much is the there. So once you do that, you can find out the momentum deficit also. These are some mathematics involved, but essentially can have a control volume, and just doing the integration would get you that. So you can go through this calculation. These are very simple calculation at the So you need to draw a control volume and then get the integration done at two different phases. So once you do this algebra, you finally get this. So you can also check in the textbooks and all these things. So one can find out the momentum thickness, which will be u by u into 1 minus 1 by u dy. So the momentum thickness is nothing. It measures the momentum deficit in terms of length. Obviously, it can also give you some kind of an what you can do. You can actually get the shear stress and all these things. So boundary layer approximations where delta, which is very small, less than the small x, which simplifies the Navier-Stokes equation, leading to the several exact solutions. And it's quite common or known is that the boundary layer solutions or laminar boundary layer flow over a flat plate which gets you the Blassius solution. So these are the solution from Blassius profile. Boundary layer approximation is applicable for high Reynolds number flow only. Additional restriction will definitely follow. Now coming back to that, some of the important findings of laminar boundary layer. So you have a uniform flow coming in, going over the boundary layer. There is a boundary layer growth, so you can find out delta by x, so which will give you the at a different location of x the boundary layer thickness or with the delta, the displacement thickness delta star, momentum thickness delta double star. All these are again these are laminar boundary layers, so these correlations are well established, so one can know. Okay, so essentially it's a self-similar velocity profile. Similarly, you can find out this delta double star, and from there you can find out the drag force. You can estimate the shear state at 1. So these are simple system or simple equations of the finding for laminar boundary layer flow over a flat plate, which you can just get it done through some integration and equating the forces with the other things. So if I put those correlations of the finding together, so my wall shear stress is going to be rho u squared d dash the start by dx. I have skin friction coefficient which can be estimated like that. I have a drag coefficient which I can drag force. Then I have drag coefficient which I can estimate like that. Then combining I can get something like that. So all these are some of the findings for laminar boundary layer profile over a flat plate, which one can estimate. So if I recall and bring things back here, my boundary layer thickness is the thickness over a solid surface or the flat plate where the velocity profile becomes 0.99 of the u infinity. Then I have the displacement thickness, which I can find out by doing integration at any point of time. I have this velocity profile, then I can integrate that. Momentum thickness, I can find similar like that. And what I have there is no pressure gradient, so del P del X 0, and also there is normal pressure gradient is 0. So that means these are the boundary layer growth or profile under 0 pressure gradient. So I have U by E equals to Fy by delta, which is a self-similar profile. I can estimate the drag force, and also I can find out the shear at the wall, drag coefficient, skin friction coefficients, and all these things. So what I can find out is the approximate solution of this. Okay, so I have this shear stress which can correlate it rho u squared d delta, and my u star is then eta. Then momentum thickness, I can write u star 1 minus u star 1 this, then delta. Then I can use shear stress, which is mu del u del y. So if this is the solid surface, so at shear stress It's a velocity gradient that y into mu. If I put that back, I get this. So then I can estimate the wall shear stress using this. So these are two things. If I equate and write down this, then I can calculate recurl. So I get del by x equals to. So you remember del double star equals to C1 delta, then you can estimate that. So you can evaluate the shear stress in this fashion. So these are some of the calculation that one can do for this. So what you can find out, that means when there is a boundary layer growth over solid surface, if you know the velocity profile, then you can find out everything. So simplest velocity profile, let's say u by u infinity is y by delta, or a theta is a plus b eta or eta. Then at y0, which is at the solid surface, obviously the velocity is zero, and y delta, it becomes the free stream velocity. This is the free stream velocity. So you find out a and b, then you can find out this velocity profile. So once you use this velocity profile, so that means as long as there is a boundary layer, so up to delta, there is a y by delta, and beyond that u equals to u. This is your capital U. Then you can estimate C1, you can estimate C2, then I can put del by x, I can do del star by x. So what I get, this ratio is 3.46, exact solution 4.91 here, 664. So you can estimate at all these things. So there are some calculations which one can always refer to. So these are exact solution which are compared with the approximate solution. So the Blassius solution approximation is 5. There is an CF into Rx, and then this is drag. So if you have a linear profile, then approximation like this. If you have a parabolic profile, it approximates very closely. If you have cubic profile, this. So the Blassius solution or the Blassius solution kind of considered to be an exact solution of Navier-Stokes equation once you apply the boundary layer approximation. So what's going to happen is that when this boundary layer profile grows, now the flow is growing. So if you see there is a uniform flow coming in, so that means now the flow is transiting from laminar to turbulent. How that happens? If you see this, so there would be a stage where you have laminar boundary layer, okay, and then you have a transition layer, and finally turbulent layer. So obviously this region, this is the viscous dominated region, and outside that obviously, so empirical turbulent flow profile could be some kind of a power law profile, and you can estimate boundary layer thickness, displacement thickness, momentum thickness, local skin friction, everything you can estimate. So just like in laminar case where we have the Blassius solution to estimate all these things, in this case also one can estimate all of this very easily. And this is the drag coefficient for flow over a flat plate with REL. That means if this is my plate, along this, this is the x direction. So along this at distance L, I have this different CD data, and using this CD data, one can estimate the. So there is common flow, which is known as cylinder flow over cylinder or sphere. But boundary layer theory can be expanded or can be extended to any geometries, including cylinder sphere. What it does, the boundary layer, is that, let's say if I have a flow like this, so when the flow comes, so flow remains attached and then it starts separating. So this is the region. So the boundary layer theory actually predicts the onset of flow separation. and then transition, lift to drag coefficient or forces. But yes, as soon as the flow separates, your boundary layer assumption fails, then that time you need exact solution due to viscous effects. So here you can see a simple example of flow separation. Here is a cylinder, and you can rightly see that the how this boundary layer separates. Then you have a separation zone where you get separated flow, and this case. So obviously this is with increasing Reynolds number. Okay. So with Reynolds number is very low, flow remains kind of an attached. That means the flow comes and around the cylinder. So this is along a streamline it goes, so that there is no separation. But when you increase the Reynolds number to 50 something, the flow separates at certain point, and then you get this recirculation or separation loss. And when you increase further, then you get this kind of an weak region or these things. So boundary layer separates from the wall when it was generated. So concept of boundary layer still exists. Approximate equation fails. So pressure gradient plays a significant role. Geometry is more important than Reynolds number. So the pressure gradient is essentially we talk about form drag, which increases necessary condition, adverse pressure gradient. That means when the flow separates like this in this region, so this is a low pressure zone and this is high. Okay. But this separation occurs because of this adverse pressure gradient. So that means dp by dx is greater than 0 along this direction. But once separated, this is so viscous region thickens. Basic assumption of boundary layer approximation becomes bit question. Now, if you look at an example like an flow through this kind of a convergent divergent section, so here is a nozzle, this is a diffuser. So when the flow comes in, you can see how the boundary layer grows, and obviously it going through the contraction, so velocity increases. Then it comes to a kind of a nozzle, and then it starts again. I mean, here you will start seeing the separation because now you are increasing the area. So the nozzle, there is a area decreasing, so it decreasing pressure, so the velocity will increasing. So this is a favorable gradient. In the throat, that is pretty much constant pressure and area, velocity is constant, zero gradient. But diffuser, area is decreasing, pressure is increasing, so velocity decreases and it becomes the adverse pressure gradient, and then boundary layer thickens. Similarly, one can see the flow over a cylinder, flow past a cylinder. So this is the cylinder surface. So the flow accelerates and then decelerates. Obviously, it goes through this favorable to adverse pressure gradient. Now, for viscous flow, adverse pressure gradient overcomes the momentum near the wall, generates inflection point and in the velocity profile. So this is a region where you see adverse pressure gradient. This is favorable pressure gradient. So this side, there would be flow separation. So you will get to see this kind of a separated zone. And this picture is very well-known picture, which is available in any textbook, internet, wherever you look at. I mean, very low Reynolds number, flow remains attached. You increase certain Reynolds number, you start seeing this kind of separated flow. At certain Reynolds number, you can get in this kind of vortex heading, which is periodic in nature. Increase Reynolds number, turbulent wake, more Reynolds number, more turbulent wake. So there is a drag versus Reynolds number plot, and you get to see the no separation, steady separation, vortex heading, boundary layer, turbulent boundary layer, and there is a drag. Similarly, one can correlate with the sports ball aerodynamics where there are dimples. This is a cricket ball. So cricket ball, golf ball, these are obviously there are flow separation happens, and that kind of makes the ball to swing for bowler to do things. So these are all example of, so same thing happens in tennis and soccer ball as well. So there are different surfaces where boundary layer separates, and their separations actually going to play a role. Obviously, when you talk about this boundary layer separation, whether it is desirable or not, but most of the time it is not desirable, because once the boundary layer separates, it's leading to higher drag. Some birds make use of boundary layer separation for long distance gliding. I mean, just some albatross can fly very long distance with near zero energy expenditure. Okay, that kind of give you some sort of an idea about this external flow, the boundary layer, and all these things. So, what now we're going to touch upon quickly the turbulence and their properties and characteristics. So, few questions that we would like to answer. What is turbulence? How do the turbulence flow behave? How can it be quantitatively described? And what are the physical processes? So this is a picture of a flow around this sphere where the friction diagram. So this is a friction coefficient across Reynolds number. You can see how it varies. So it's again different Reynolds number very low, Reynolds number at high, and then there is a sudden drop in the friction factor, which is known as the drag force, or even drag crisis. And obviously the drag force one can estimate like this. Similarly, you can see this is a Reynolds number that 15,000, this is 13,000. But interestingly, that means this Reynolds number to this Reynolds number, your inertia has gone up, so you have a higher level of turbulence. So turbulence is actually reducing the overall drag, because behind this blob body, if you have a less separated zone, this is a high separated zone, so this will have higher drag. So that means one of the advantage of the turbulence is that it can reduce drag. Some other example of turbulent flows, this you can see in the volcano. This is the ash plume at a very height. So these flows are happening in nature, and they are highly turbulent. There is another, this is a smoke from cigarette. This is an downwash of the aircraft when it is flying. So you can see these are, I mean, these things one can see in nature. What is important of the turbulent flow is the scale similarity. So that means small scale structure for different Reynolds number. So this is Reynolds number 4300. This is 10 to the power 7. If I zoom in the views, you can see this nature is pretty similar. So that's the important characteristics of the scale similarity. That means the Reynolds number changes, the intensity changes. This is where transition to turbulence happens. So this is a top view of an experimental picture. There is a nice uniform flow, goes through the boundary layer growth. So it goes through transition, then transition, it becomes completely turbulent. This is a Reynolds number. I mean, it's a jet. You can see it's a 1500 and 20,000. So increase in Reynolds number, range of scale with increasing Reynolds number. That means you see the structure here and you see the structure here. So once you increase more and more this kind of an, I mean, the inertia effect or the Reynolds number effect, you get to see. So this is to characterize at a particular point the turbulent flow behavior looks like. So it is more like an instantaneous randomness in the flow field. Okay, so that is how. So if one has to define that turbulence flow field, so obviously it's a fluid motion where velocity, pressure, and other flow quantities are fluctuating or fluctuate irregularly with time and space. So the turbulent fluid motion is an irregular condition of fluid in which various quantities show randomness. So essentially it's a randomness is the system. So turbulence is due to formation of point or line vortices on which some component of the velocity becomes infinite. So this is Jane Leary who quoted that. So if we put them together in slightly different ways, so the turbulent flow, these are essentially unsteady and very irregular or chaotic motion, which is transported quantities like mass momentum. So one can identify swelling patterns, enhance mixing. So here the fluid properties exhibit random variations. Their statistical averaging results get to some measurements. Characteristics allow for turbulence modeling. Then wide range of turbulence scales or the ADs. Actually, the what happens in turbulence in there is a energy cascading that takes place. So that means primarily the large scale structure are very much geometry dependent, and then they breaks down to the smaller structure, and then finally it comes to a small structure where it gets through the viscous dissipation or so this is where the energy cascading. So this is called energy cascading. So that means large scale structure to small scale, medium scale to small scale, small scale. That's how that happens. The properties of this turbulent flow, if I have to talk about, they are unsteady and three-dimensional in nature, essentially. There are irregular and chaoticness, characterized by vortices structures or ADs or things like that. There are different length scale. There are large scale structure which are known as macro structure, and they are most of them are dependent on the geometry. There are small scale structure which are known as the microstructure. These are essentially energy dissipation universal in nature. Turbulence are often characterized at the high Reynolds number, so the inertia effect is very dominant. They are dissipative in nature. That means there is a rapid loss of energy. Just now we talked about the energy cascading process. It allows the effective in mixing, enhances heat and mass transfer. So how one can look at the turbulent flow, whether the flow is turbulent or not. So you can look at the non-dimensional number like Reynolds number and try to identify based on whether the internal flow or natural convection or external flow. You have to characterize based on the Reynolds number. If it is beyond certain limit, then the flow is considered to be turbulent. Obviously, then it shows the property of the physical property of the turbulent and all. So these are a very, very idea about the turbulent flows and things like that. Because this should be required when we talk about the wind turbines and all these things. But any other details of this flow field and things like that, you can actually refer to the textbooks and read. Okay. So that much, I mean, that's pretty much would like to cover or refresh your basic idea about fluid mechanics, turbulent flows, and all these things. Now we'll move to the slowly the discussion on the wind turbines, technologies, and all this.